Welcome everyone to our third workshop. Today's topic is going to be over divisors and Roman numerals. Um, Especially for these two topics, we highly recommend that you guys do take notes because these two topics are fairly new and are a bit difficult to grasp at first. But with the notes, you guys will be able to use and practice examples that we go over and also the Kahoot that we'll play at the end. Oh, and also, if you have any questions, just feel free to ask anytime. So now, in this workshop, we also have two more mentors. We had them in our last workshop as well, but we didn't really introduce them. So in this one, we wanted to formally introduce them. So we have two new mentors. We have Iman and Abi, and they're both rising sophomores. And yeah, we're really glad that we have them on our team now. So just the layout of this workshop. So we're first just going to be going over what Roman numerals are, just about them, their history, and then we're going to be going over their rules, and then we're going to be doing practice with that, and then we're going to move on to our second topic, which is known as divisors or PID, which stands for positive integral divisors, and then we're going to do practice with that topic, and then we're going to move on to our Kahoot. So a little bit of Roman numerals history. It originated from ancient Rome, as you may already know. There are 7 symbols: I, V, X, L, C, D, and M. They were first used around 900 and 800 BC, so about 3,000 years ago almost. And they were created so that Rome could have a common method of counting that could be used in trading and just overall communication, and really just for a first form of communication, because before that there wasn't really any form of communication in Rome. So how Roman numerals are used today. Roman numerals appear in building cornerstones, movie credits and titles, ships, which are like the names like Queen Elizabeth II, and sporting events like the Olympics and Super Bowl. Roman numerals also appear in some jobs as well, which include astronomy, and astronomers use it to designate moons like Titan 3, Titan 4. Chemists use it in the periodic table for like all the elements. Writers use it in the table of contents and scripts to like numbers, like lines or etc. And then music theorists also use it in notation symbols. Reading Roman numerals. So there are 7 symbols, like I said before. So I is 1, V is 5, X is equal to 10, L is equal to 50, C is equal to 100, D is equal to 500, and then M is equal to 1,000. So a way to sort of remember these is, so I, V, and X are commonly known, but a way to remember those is I, it's just like one finger, and that's 1. V could represent your hand as 5 fingers, like your hand sort of like in a V shape. X is just 10, like I think if you put both of your hands together, like cross, you have 10 fingers, so that's that. And then with C, so C like century, and century has 100 years, so that's how you could do that. And then with L, just remember that L is half of C. For M, millennium, meaning 1,000 years, and then M equals 1,000. And then for D, just remember that D is half of M. So rules. So basically, when writing Roman numerals, you can't have 3 of the same symbols in a row. So if you want to, so for example, 3, you can have 3 eyes. That's good. But you can't have 4 eyes, because that's more than 3 of the same symbol. So yeah, you can't do that. And these are basically just some examples of fake Roman numerals. So you have IVI, and another rule for Roman numerals is that you want to make sure to have your symbols grouped together. So you see how I is separated by the other by I by a V. So the I should be connected with each other. So it could be VII, but not like this. And then same sort of format with LCL. The L's are supposed to be next to each other. And then the bottom one, sorry you can't see that, but it's four V's. Yeah, it's four V's. So and you can't have more than three of the same ones. And also, when writing Roman numerals, you want to be as most concise as possible. And this meaning you can't have extra or just not important symbols. So like for example, let's say you want to write 10. Well, you can't just write two V's because there's already a symbol for 10 and that's X. So that's what I mean by concise. You want to write your Roman numerals with the least amount of symbols as possible. So yeah, numbers like 4, you can't have, 4 ones. That's just not allowed. But to counter this, what you can have is you can place smaller Roman numerals before the greater ones. For example, for 4, you can't do I, but you can do IV, which basically means 1 before 5, which is 4. So yeah, so 1 before 5 is 4. And another way to think about it is that whenever you have a smaller Roman numeral before a bigger one, you just want to, it's sort of like subtraction. You just do 5 minus 1, you get 4. So whenever there's a smaller behind a bigger, just no subtraction. Okay, so I'll just go over these practice examples with y'all. Alright, so the first one, VI, well V is just 5 and then I is 1, so 5 plus 1 is just 6. IX, so like we said before, since I is before the X, this means subtraction, or 1 before X, which is just 9. And then DI, well D is just 500 and I is 1, so that's just 501. And then CV, well C is 100 and then V is 5, so it's just 105. So some harder examples. So CLI is 151. So C is 100, L is 50, and then I is 1. And then MMXC, so the two M's equals 1,000, and then X before a C is 90, because C is 100, but then there's a smaller one behind it, meaning subtraction. Or you could think of it as 10 before 100, which is 90. And then with the same sort of thing with the third one, X is before L, which is smaller. So you could, and L is 50, so X before 50 is, or 10 before 50 is just 40, and then you have the I at the end, which is just 41. And then, so another thing to know is that Arabic numerals are just known as normal numbers. So like the examples that we just did are examples of converting Roman numerals to Arabic numerals. So Arabic numerals it's just like a fancier way to say normal numbers that we normally use. So these right here. Now with Roman numerals, like with normal numbers, you could also do operations such as addition, subtraction, multiplication, or division. But the most common ones are the most common on a test are usually adding and subtracting. So for example, you have mm minus d. Well, so a way to think about this is first just convert these numbers individually into real Arabic numerals or normal numbers. So is just 1,000 minus d, which is 500. So 2,000 minus 500 is just 1,500. And ix is 9. So because 1 before 10 is 9. And then times C is just 100, so 9 times 100 is 900. Now, you guys try these. Yeah, and just make sure to try to have them in the same line. That way you don't have to send individual text too many times. Alright, so for the first one, you have CCIX. So basically, CC is 200, because c is 100, so there's 2 of them, so 200, and then ix is 1 before 10, which is 9, so 209. The second one, operation, so 100 minus 150, well, that's negative 50. And then third one, x is 10 times LV, which is 55, because L is 50, V is 5, so 10 times 55 is 550, and this is just converting it into normal numbers, so that's M, so that's 1,000, 500, 600, 700, yeah, 1709, so M is 1,000, D is 500, and then these two hundreds equals 1700, and then IX is 9. And then M divided by D is just 1,000 divided by 500, which is 2. Alright, so that was it for Roman numerals. Now we'll be moving on to divisors, which is our second topic, also known as PIDs. Alright, so there's two things you can do with PID questions. One is you want to find the number of PIDs, and the other is finding the sum. So what PIDs are so they stand for positive integral divisors, and these are basically all the numbers that can be evenly be divided by a specific number. So for example, let's say you have 28. Well, 28 has 6 PIDs because 28 can be evenly divided by these 6 numbers, 1, 2, 4, 7, 14, 28. 28 can be evenly divided by all of these. And since there's 6 of them, that means 28 has 6 PIDs. So that's what a PID is. Now, whenever you want to find the number, a way to do this is first you have to take the prime factorization of the number. And then once you have the prime factorization, with the exponents you have at the end, you want to add 1 to each of them. And then you just want to multiply the added exponents together. Now, I know that may have not made too much sense, but I'll cover that in the example next. Alright, so let's say you're given this question, how many PIDs does 45 have? Well, first you want to take the prime factorization of 45, so this is basically a factor tree, and you're basically simplifying 45 into numbers that are prime. So you have 5, 3, and 3, and notice all of these numbers are prime, and once all of the bottom numbers are prime, you know that you've completely prime factorized the number. So the amount of numbers that you have here determines what the exponent is. So since there's 1 5, the exponent is 1, and since there's 2 3s, the exponent is 2. Now, once you have the prime factorization form, now you can look at the exponents and add 1 to each of them. So you have 1 here, so add 1 to that is 2. You have 2 here, so add 1 to 2 is 3. And now that you have these two numbers, 2 and 3, you can just multiply them and get 6 PIDs, and that's it. Now, why does this work? I think it has something to do with a probability and counting theory. I'm not too sure of the specifics, but something where there are n+1 choices for each prime to create a divisor. Just something complicated like that. Now, examples. So let's say you're given to find the number of PIDs of 54. So first you want to take the prime factorization, and that's just 2 times 3 to the third power, or meaning 2 times 27, but you want to prime factorize that 27. And then now that you have the exponents, you can just add 1 to each of them, so you have 1. So whenever there's not an exponent, there's always an exponent of 1, because any number to the any number raised to the first power is just going to be the number itself. So that's why they don't usually write the exponent here, but just know it's always going to be a 1. So add 1 to 1, you get 2. Add 3 to 1, you get 4. Multiply 2 and 4, you get 8. And that's the answer. And 8 basically means that there are 8 different numbers that 54 can divide, or that can be divided into 54 evenly. Now for 20, do the same thing, just find the prime factorization. You get 2 squared times 5, add 1 to each of the exponents, so you get 2 plus 1, 3, 1 plus 1, 2, 3 times 2 is just 6. And a same sort of concept, there are 6 different numbers that 20 can be easily divided into. Or yeah. Now you guys try this one. So for 28, what you want to do is you take the prime factorization, so that's 2 squared times 7, and then add 1 to each of the exponents. 2 plus 1 is 3, 1 plus 1 is 2, and you get 3 times 2, which is 6. So that's the number of PIDs of 26, 6, also meaning there are 6 different numbers that 28 can eat that can be divided by 28. And then for now find the number of PIDs in 1,000. Okay, so first just start off by taking the prime factorization, and that's just 2 to the power of 3 times 5 to the power of 3. And that's just another way of writing 8 times 125, which is 1,000. And notice that both of the exponents are 3, so you just add 1 to both and you get 4 for both, and then you multiply them together, you get 16, and that's it. Alright, now you're also wanting to find the sum of PIDs. So that was finding the number, but the sum is now you're taking all the numbers that you found earlier, but now taking the sum of that, taking sum of all those numbers. So first what you want to do is just start off by taking the prime factorization again. So prime factorization is a pretty important concept for PIDs, so it's best to get familiar with this. Okay, so once you take the prime factorization, so let's look at 28. You take the prime factorization, you get 2 squared times 7. Now you want to so 2 squared and 7 are separate terms. And now you want to individualize each term and apply steps 2 and 3 to if they follow. So let's start with 2 squared. Now, step 2 says if the exponent is 1. Well, the exponent is not 1, so let's just go to the next step 3. Now it says if the exponent is greater than 1, do the following formula. So 2 squared has an exponent that's greater than 1. So you want to do this formula right here. So n is basically the base, so 2. So let's do that. So the formula for 2 squared would be 2 raised to the exponent plus 1, so 3, and 2 to the third power is 3, or 2 to the third power is just 8, and then you minus 1, so that's 7, divided by n minus 1, which is the base minus 1, and the base is 2, so 2 minus 1, and then 7 divided by 1 is just 7. Now, whenever the exponent is 1, looking at the 7, which has an exponent of 1, it's actually really easier. All you have to do is add 1 to the base, and the base is 7, so that's just 8. And now that you have these two numbers, you have 8 and 7, all you have to do now is multiply them, and you get 56. Alright, so what this is basically a formula of what we just did. And we just added this in here showing you guys, or just proving the concept that what our biggest goal is to teach you guys seemingly difficult math concepts that are actually easy and pretty easy or simple in reality. So looking at this equation at first, you might be really confused at what to do. But what we just did is basically this equation right here. So that's why it's sort of amazing how complex an equation can be, but when you actually do it or have another method of doing it, how easy it can also be. So yeah, it's just a cool little thing. Now you guys try this one. Find the sum of the PIDs of 16. And then next try the sum of the PIDs of 20 once you're finished with 16. Alright, so looking at 16, so 16 when prime factorized can be written as 2 to the 4th power, because that's just what 16 is. And now, looking at here, you only have one term, so you only have to do one action. And so looking at the exponent, it's greater than 1, and when it's greater than 1, you have to use that formula that was on the previous slide. And that formula was the base raised to the exponent plus 1, so 5, and 2 to the 5th power is just 32, and then you want a minus 1, which is 31, divided by n minus 1, or 2 minus 1 in this case, and 31 divided by 1 is just 31. So the answer is just 31. Now, looking at 20, you have, just take the prime factorization again, you have 2 squared times 5, and then you want to, so you have two terms, so let's start with 2 squared, and since 2 squared has an exponent greater than 1, you want to do that formula, which this formula again, and with that formula, you get 8, you get 7, because 8 minus 1 is 7, and then that's one number, and then for the 5, you just, since it has an exponent of 1, all you have to do is add 1 to the base, so 6. So you have two numbers now, 7 and 6. Now all you have to do with those two numbers is multiply them to get 42. And again, these two numbers, 31 and 42, they basically mean that whatever the PIDs, so the number of PIDs that you had here for 20, whenever you add all those up, you get 42, and then same thing with 16. Now, there is a second method of doing this. So it's more of a preference thing. If you like this one, then stick with this. If you like the first one, then stick with that. So again, you want to find the prime factorization. Now, okay, so with this one, what you're basically doing, so looking at 30, you have, once you prime factorize it, you have 2 times 3 times 5, and that's the prime factorization thing. Now, what you want to do next is, similarly, you want to individualize each term, so 2 and 3, 5 are separate terms. So there's 3 total terms, and you want to sort of individualize them and group them in parentheses, and inside those parentheses, you basically want to start off with so let's start off with 2, and you want to start off with whatever the number is here, whatever exponent is here. So again, like I said before, whenever there isn't an exponent, there's usually always a 1. So this is 2 to the first power, because that's what it starts with. And then you want to keep going, you want to keep adding by the same 2, but you want to have the powers descending by 1. So it starts off with 1, but then it goes to 0. And then same thing for all the numbers. So 3 starts off with 1, goes to 0, and then same thing with 5. Now let's say if this was 2 squared, then you would just start off with 2 squared, and then you would plus 2 to the first power plus 2 to the 0. So you're just basically going in descending order by the powers. And yeah, that's how I like to think of it. And then once you set this up, once you set all the descending powers in order, you just want to add them. So 2 to the first power is 2, 2 to 0, and anything to the 0 power is 1, anything. So this would be 1, so 2 plus 1 is 3, and then 3 plus 1 is 4, and then 5 plus 1 is 6. And then once you have these numbers for each of the term, you just multiply them out and you get 72. And then you do the same sort of thing with 24, so prime factorize it, you get 2 cubed times 3, and then you want to write them, like group them individually, and add them in descending order. So start off with 2 to the third, because that's what it starts off with, and then go to squared, and then up to the first, and then 0. And then just add them all up, and then you get 15 times, you get 15, and then same thing with this, just go in descending order, 1, 0, add them up, you get 15, 4 times, when you multiply those, you get 60. Now, you guys tried these. So for 54, using that method, so first just find the prime factorization, and you get 2 times 3 cubed. And then you want to do that descending order thing with each of them. So you have, this is just a bit rearranged. So they just started from 0 and then to 1. So 2 to the 0 is just 1. 2 to the first is 2. Then you have those two. And then do the same thing with 3. So 3 to the 0 is 1. 3 to the first is 3. 3 to the second is 9. 3 to the third is 27. Add all them up individually or within the bracket in parentheses. And then once you get the sums, then you just multiply the sums to get 120. Now, same sort of thing with 200, just find the prime factorization. You get 2 cubed times 5 squared, and then do the descending order thing. So start with 2 cubed, then go down 2 squared, then the 2 to the first, and 2 to the 0, and then do the same thing with 5. And then you're left with 15 times 31, and once you multiply that out, you get 465. All right, yeah, that was it for this workshop. Now for resources, for those that may be confused about Roman numerals, this is a pretty good video to watch, and I do recommend it. I know it helped me a lot when I watched this when I was your age. Okay, so like always, we'll always have our optional worksheet for each of our workshops. So we'll have 10 number sense questions on the worksheet and 5 A+ math questions. And remember, it's completely optional. It's just, you don't have to do it, but it's just for extra practice for those who may want to. Okay, so now I'll just briefly go over the Kahoot. All right. So this is a Kahoot. So the first question, how many symbols do Roman numerals have? That's just 7. Which of these is a Roman numeral? So V is a Roman numeral. It stands for 5. M is equal to 1,000. So like M is millennium or however you pronounce it. Yeah, so it has 1,000 years. So M is equal to 1,000. V is equal to 5. C is equal to 100. That is true because C is like century and century has 100 years. D is not equal to 10,000. D is, remember, half of M, so 500. So that's false. Now they just want you to convert these into Roman or Arabic numerals. And so MMC is just 2,100. And then MDC, so M is 1,000. That's 500, 600. And then, so that's 1,600. And then this whole thing is 17 because X 10 and then 7, 17, so 16, 17. Now operations, so 1,000 minus 400 because 100 before 500 is just 400, so 1,000 minus 400 is 600. And then DIX minus IX, so D is 500, IX is 9, 1 before 10 is 9. So you have 509 minus 9, which is just 500. For 11, just you have 3 C's, so that's 300 times XV, which is 15. So 300 times 15 is just 4,500. A way to do that a bit quicker is, or easier, to make it easier for you, 300 times 15 might be a bit hard at first, but all you have to do is just remove the zeros, so just treat it as 3 times 15, so that's 45, but then add the zeros back in later to get 4,500. And then IV plus L, that's just 4 plus 50, so 54. Now this is a bit of order operation, so you may have heard of CHEMA or PEMDAS, those type of acronyms or whatever. And so you want to start with what's in the parentheses. So 1,000 divided by D, 500 is 2, times that, which is 12, is 24, times 100, which is 2,400, plus 50 is 2,450, so it is true. Now on to PID. How many PIDs does 145 have? So what you want to do first is take the prime factorization, which would just be 29 and 5. And since 29 and 5 are already prime, you can't do anything else with it. So now you want to look at the exponents, and the exponents for both are just going to be 1 since they're prime. So add 1 to each of the exponents, so that's just 2, and for both, and then do 2 times 2, and you get 4. And then same sort of thing with this. So this can be written as 2 squared times 3 squared. Yeah, 4 times 9. And then add 1 to each exponent, so that's 3 times 3, which is 9. Now onto the sum. So the sum of the PIDs of 100. So with the sum, you want to prime factorize it, and that's 5 squared times 5 squared times 2 squared, and then this one's a bit nasty since you have to do that weird formula, that long formula with like n to the raised to the n plus or exponent plus 1 for both, so that can be a little tricky. But once you do those two formulas for both 5 or for both of the terms 5 squared and 2 squared, then you should get 31 times 7, which is 217. Now this is a speed round, so it'll be less time, but for the same type of questions. So MLIV, that's 1,000 and 50. L is 50, and then that's 4, so 1,054. And then DL divided by XI. So DL is 550 divided by XI, which is 11. So 550 divided by 11 is 50, also known as L, written as L in Roman numerals. Now back again at order of operations almost. So L divided by X, 50 divided by 10 is 5 times X is 50 plus 100 is 150. And then the number of PIDs of 24, so you want to do that prime factorization thing, so that's just 2 squared times 3 to the first, and now you want to add 1 to each of the exponents, so that's 2, or that's 3, or sorry, hold on. So when you prime factorize 24, it's 2 cubed times 3 to the first. So now you can add 1 to each of the exponents, so you get 2 cubed to 4, and then the 1 to 2, so that's 4 times 2 is 8, not 6, so it's false. And then for 21, so for the sum of the PIDs of 9, so this number is pretty small, and you know that PID are all the numbers that can be divided evenly by 9, and you know that that's 1, 3, and 9, that's it. And then it's wanting the sum, so you just add 1, 3, and 9, and you get 13. So that's a quicker way of doing it, but you could also do the original normal method. And then the last question, just a bit of a throwback. 15 squared is just 225. Yeah, so that's it for the workshop. And